Welcome back to our very final topic of this course. It's called Statistical Inference, not for the means or for proportions, but it is for regression. You may remember from several months ago, we talked about two quantitative variables and the relationship between the two. And we focused on a linear relationship. And if it was power or exponential, we linearized them using logs to focus on linear relationship between two quantitative variables. We talked about the association between those two variables, the correlation, and the whole purpose was to make not statistical inference, but to extrapolate and predicts the future based on a regression line. Today we are going to begin a conversation about inference on regression. Of course, we are going to address the confidence intervals and testing or hypothesis testing for linear regression. But today we're just going to have a quick introduction. I'm going to split this concept into maybe 2 or 3 parts so that it is a lot more digestible. So we're not going to do any inference today at all, but I'm just going to introduce you to the concept. So here is what we did back in October or September. We had 2 quantitative variables. I chose today to focus on number of cars a family would have based on the size. And I'm thinking maybe there is a positive association. In other words, the bigger the size of the family is, the more likely they're going to have more cars, right? So both are increasing or both are decreasing. You don't have any increasing and any decreasing at the same time. And what we did many months ago, we focused on one of these lines, either the blue or the red or the black. We took, maybe it was our class of, let's say, 10 students or 11 or whatever. And we asked each person, what's your family size and how many cars do you have? And we plotted those points. Let's just focus, let's say, on blue. And then we used mathematics to draw the best fit line. We used the least square regression line, which is a line that minimizes the distance between those blue observed values and the actual line. So we created squares when we minimize the sum of the squares. So that's how mathematically we came up with an equation of a line. And once again, so that we can extrapolate. So if I have a family size of, let's say, 7 people, I can predict based on the blue line how many cars they would have. Of course, you don't want to extrapolate too much. You have to extrapolate within reason. And you may also remember A was the y-intercept, like here, and B was the slope of the line, which is the number of cars per family size. Okay, and we put a hat because we are actually predicting the number of cars. In other words, if I have an X value here, and let's focus on the blue. If I have an X value here, I have a family size of, let's say, 3 right there. I can quickly tell the number of cars they have because somebody told me. So that was an observed value. But based on the regression line, the Y value will be here. It will not be here. And that's why we put a hat to differentiate between the observed and the predicted. I made a small mistake here. I said number of cars per family. That looks like a slope. I really meant to say just number of cars. So given a family size of, let's say, 3, if I focus on the blue, I can go here and say, okay, they have 4 cars or whatever. I hope they don't have 4 cars if they're a family of 3. Cars are liabilities. You shouldn't buy cars unless you have to. Okay, so what we're going to do today is pretend we are interested to know the number of cars, to know whether or not the number of cars and the family size are linearly related, and then we want to do statistical inference on them. So let's say we are interested in asking everyone at the school, And so what we do here is we take a sample of, let's say, 10, look at the blue, and we ask people how many members of the family and how many cars you have, and we record those blue lines, and we drew the best fit line based on chapter 3. And then we took another sample, let's say it's called the red, and so if I take another sample of 10 people, there might be a repeats from the previous sample, and we ask them the same questions. What's your family size? How many cars you have? We record them, and then we drew the best fit line. So that's chapter 3, chapter 3, chapter 3. And you can do it over and over and over. I just did it 3 times, but I could do it like 20 times, okay? And what we want to do is, based on these samples, we want to be able to draw a conclusion about the entire population. So let's say these are all the people at the school, and we asked every single one of them, what's your family size and how many cars do you have? And let's say we actually know the truth, okay? So, and then we're going to do the best fit line. This time, we're not going to call it A and B, we're going to call it alpha and beta. So alpha and beta are the parameters of interest, and A and B, I call them A1, A2, A3 because I have 3 separate samples, but the little a's and the little b's are your statistics, right? Your statistic. So based on a sample, we want to do statistical inference to draw a conclusion about the population. And what we are going to focus on in this chapter is on the slope only. So in the past, you remember, we talked about X bar versus mu. So this was my statistic. The distribution of X bars was a normal distribution according to the central limit theorem. And we were trying to draw a conclusion about the parameter. We also had a sample proportion versus the sample versus the proportion of population, and we concluded that, let me write here, statistic. This is the parameter that generally we don't know, and we are trying to predict using one of the statistical inferences. Well, it turns out that we can also use a little a, like these A1, A2, A3. Not little a, but I'm going to focus on the slope. So we're going to focus on little b to predict beta, the slope of the population, okay? It turns out that the expected value of b is beta. In other words, a little b happens to be an unbiased estimator of beta, because the mathematics shows me that the expected value of b is beta, just like the expected value of X bar was mu and the expected value of P hat was P. Now, generally, when we talk about the mean or the expected value, we talk about standard deviation. I'm going to hold on to that one for a moment, okay? At least for today. So the next thing I want to do, and we're not addressing inference at all today, is to check the conditions. Now, you are familiar with definitely 3 conditions here that you've seen over and over and over again. And they were here, I'll put them in blue, was this condition here, and this condition, and this condition. We have used these 3 conditions when we did statistical inference for both the proportions and for the means. Well, for this particular concept, there are 5 conditions total. So I'm going to address them quickly, and then we will conclude this short video. The very first condition And the acronym is LINER, like linear without A. That's how you remember them. There are 5 of them. So you always have to check these conditions before you proceed to do statistical inference. The first one is that Y and X are linearly related. In other words, if you believe that the number of cars and the family size are not linearly related, let's say they give me this curve, then there is no need to do statistical inference because they need to be close to linear. They don't have to be perfectly linear, but they have to have that trend of linearity, like this one. I mean, it's not great, but a line here would be probably a good idea. So that's the first condition. Y and X are linearly related. Generally, sometimes it's very hard to test this because you actually, if you can test it, then why do statistical inference? If you already know the answer and you know that it is linear, I don't even know why you want to rely on samples, right? Take a sample, take a sample, take a sample. I took 3 samples, but I could take 20 samples to do statistical inference to get this if you already know the answer. So generally, like especially on the AP, they say assume that Y and X are related linearly. The second condition, I, stands for independence, that the data is either collected with replacements. So you take a sample and you, like in my case, I took a sample of 10 in blue, and then I put them back in the pool. So some of them might be picked again, right? If that is the case, then you don't need to check the 10% condition. If they are collected without replacements, then you must check the 10% condition, basically to say that no more than 10% of the population is the sample size. So for example, in here, if I took a sample of 10, well, I would assume our school has 100, at least 100 students. If it has less than 100 students, then a sample of 10 is not sufficient. Then the 10% condition is not fulfilled. So again, either that the data is collected with replacements, which means everyone has an equal chance of being picked all the time, or if it is without replacements, we know that the probabilities are going to change, and therefore there's dependence. And for that reason, you check the 10% condition. The third one, I'm going to skip this one and this one for a second. The third one is also obvious, right? How did you collect your data? How did you pick these 10 people? How did you pick these 10 people? How did you pick these 10 people? Did you do it out of convenience? You just stood by your dorm and asked the 10 people that came out from the dormitory? Because that wouldn't represent the population of interest of, let's say, 1,000 people here, right? So make sure that the data is collected properly. It comes from a well-designed sample. Could be an SRS, could be stratified SRS, could be systemic sampling. You just have to make sure that the data is collected in such a way that it represents the population of interest. So that leaves me with these two. You're familiar with this concept, even though it has a different take. We have a different take on this one here. So you're familiar with this, but this is kind of new. So I'm going to address these two with this picture, which is in your book, by the way. So here is what happens. Let me go back here. So let's say I took 3 samples, okay? And hopefully you'll take many more samples. And each sample, I think I had 10, but maybe you'll have a sample of 20. I don't know. I just didn't want to have too many dots. What it says here is for any, I'm going to write, for any given, let's say X, for any given X, let's say you focus on a family size of 4 people. If you focus on a family size of 4 people, now clearly, every time you take a sample, you might have a different y-intercept and a different slopes, right? Look at the slopes here, the y-intercept, they're different. And look at the slopes. I mean, they're not parallel, so they have different slopes. And that's to be expected. But if I focus on a family size of 4, let's say, and you're not going to change x anymore, the y values, the number of cars, so according to the first sample here, the black one, that's the number of cars, and then that's the number of cars for this sample, and well, I have 2 here, but let's say this one, that's the number of cars for that sample. Those number of cars based on this family size have to be normally distributed. We know they're going to be different, as you can tell, right? Those heights are different. But they're not just different. They actually follow a normal distribution. If you plot them, let's say I do 20 lines, okay? 20 lines because I took 20 samples of 10. Those dots, based on x equals 4, when you plot them, they might begin to look something like this. Right? They look symmetric and hopefully they follow a normal distribution. This is like a dot plot, okay? So that's the idea, okay? And so let me go here and show you. I had to do it in 3 dimensions because I have to draw the normal distribution. This is the xy plane, okay? It's just normal xy plane. These are perpendicular, okay? And so for a given x, let's say x1, for a given x, different values of y, for a given x, you're going to get different values of y, right? Because you took 3 samples. But if you took 20 samples, you'll have 20 points. Those points will follow a normal distribution. And then if you pick another x, let's say the number of cars now is, let's say now I pick a family size of 2 or a family size of 5, okay? So if I pick a different family size, the number of cars across those samples I took follow a normal distribution. That's where normality comes in. In case you wonder, what are you talking about? You're telling me that x and y are linearly related, and now you're telling me that they follow a normal distribution? You need to pay attention to the subject. Here it says x and y are related in a linear format. Here it says for a given x, so x is fixed, it doesn't change, the y values follow a normal distribution. So these are not necessarily contradictory, okay? You just have to pay attention to the subject that we're addressing. Furthermore, those normal distributions, they have the same size, the same shape. In other words, you don't have one like this. You don't have one like this and one thinner or one flatter. They have the same standard deviation. If you focus on them, so this is the points of inflection, that standard deviation, and let's say this is the points of inflection, and let's say this is the points of inflection where the curve changes the curvature from concave down to concave up or vice versa. That sigma right there has to be the same. In other words, the opening of this normal distribution is the same. Just pretend, a slew of cars are driving through, this bridge. Think of this as a bridge. That bridge has to have the same height, the same width, the same everything. Can't have one that is 4 by 6 and another one that is 3 by 11 or something. They have the same distribution, okay? So that's where this condition comes in. Equal variance. Equal variance means equal standard deviation. Because if the variances are the same, that means the standard deviation is the same, because the standard deviation is just the square root of the variance. So all of those distributions have the same variance, which means the same standard deviation. So that's where these two come from, this picture here, okay? So I'm deliberately not going to do much today, just to get you an overall view of what this chapter is about. We haven't done any inference whatsoever. I just want to give you the big picture of what is to come, okay? And it's not a difficult subject. In fact, they oftentimes give you alpha and beta. in a box. There isn't a lot of math to do, but conceptually, sometimes it is hard, especially this one. It's kind of hard for a student to conceptualize. So take a look at the book after you watch this video, and I will see you next time.